So here are some definitions we're going to try to use from time to time regarding our sequences. First definition is that a sequence is increasing if every time you get to a new term in a sequence, it is going to be greater than the previous term. Now there are a couple different ways that you can do this. You can either algebraically set it up like you see. So algebraically, you could say that you set up this inequality and manipulate it algebraically until you arrive at something that is very clear and obvious. There's also a calculus way to show that something is increasing. Now, what we're going to do is introduce the concept of a generating function. The generating function for a given sequence is basically take all of the n's and turn them into x's and refer to that as f of x. So if f of n is equal to a sub n, then f is called the generating function. The way that you can prove algebraically that a sequence is increasing is show that f prime of x is greater than 0 for all x being greater than 0 as well. Now, related definition, a sequence is decreasing if later terms are less than their previous terms. Algebraically, you would set up this inequality and manipulate it into some sort of tautology. Tautology is something that is always correct, or identity would probably be a better word for that. As far as calculus is concerned, the way that we show that something is decreasing is once again find that generating function and prove that it is less than 0, or excuse me, show that the derivative is less than 0. If a derivative is less than 0 for all x being greater than 0, then you have shown that the sequence is always decreasing. Now, in the event that you have shown that something is either always increasing or always decreasing, then what you have is referred to as a monotonic sequence. So this is a sequence that is always increasing or always decreasing. If that ever changes, then it is not considered monotonic. Keep in mind that the prefix mono means one, and if the sequence only does one thing, either always increase or always decrease, that's what makes it monotonic. Now some other definitions that we're going to be using for purposes of sequences. Bounded above means, well, first off, suppose that you have a sequence that takes on the following form, a sub n. It is bounded above if there exists a number, we'll call it capital M, such that, and in order to be bounded above, capital M serves as what we call an upper bound. That'll be for all n being greater than or equal to 1. Bounded below is essentially the opposite. There exists little m such that a sub n is greater than or equal to little m for all n being greater than or equal to 1. If something is both bounded above as well as bounded below, then we refer to it as bounded. To give a quick example of the things that we have been working with so far, I would like to consider the following sequence. The sequence I'd like to consider is n over n plus 1, and we'll start this bad boy off at n equals 1. So just to throw some terms out here, for n equals 1 we would get 1/2, for n equals 2, 2/3, for n equals 3 it'd be 3/4, For n equals 4, 4/5. For n equals 5, 5/6, and so forth and so on. What we're going to do is show that this thing is monotonic, as well as bounded above and bounded below. So, to show that this thing is monotonic, what I'm going to do is define the generating function by changing all of my n's into x's. Then I'm going to use the quotient rule to take the derivative of this thing. So f prime of x is going to be equal to low d high less high d low over the square of what's below. Combining like terms in the numerator tells me that this is going to be 1 over x plus 1 quantity squared. You'll notice that the numerator is positive 1, and the denominator is something that is squared, which is guaranteed to be greater than 0. So regardless of the value of x that we plug in here, so that's for all x being greater than or equal to 1, or I suppose we could even say for all x greater than 0. The important thing is we got that the first derivative is positive, therefore the sequence is increasing. And you'll notice that the value of the fractions is getting larger. This is 0.5, 0.6 repeating, 0.75, 0.8, 0.83 repeating. So yeah, the fractions are getting bigger. As far as bounded above and bounded below are concerned, I guarantee you that 0 will bound this thing below. The reason is, back in the original definition of the sequence, we started with a positive number and allowed it to continue to get larger. So this would be a positive number divided by a positive number. 0 is definitely going to be smaller than every single number in this sequence. I'm also going to make a claim that this thing is bounded above by 1. And here's how I can support this claim. I'm going to put n over n plus 1, and I'm going to go with the definition of bounded above and say that this thing will be less than or equal to 1. The way that I'm going to prove this is multiply both sides by n plus 1. We will get n is less than or equal to n plus 1. And finally subtract n from both sides. Subtract n from both sides. We wind up with the statement that 0 is less than or equal to 1. Because this statement is true, this statement becomes true, and because this statement is true, this statement becomes true as well. Now, those are by no means the only bounds that we could use. We could also say that this thing is bounded below by -50. We could also say it's bounded above by 9001. The number isn't the important part. The important part is whether or not it actually is bounded. That is because there is a very crucial theorem where we take all of these things and we put them together. The theorem states the following. This is the monotonic sequence theorem. The monotonic sequence theorem states the following. Every bounded monotonic sequence is convergent. Convergent. Every bounded monotonic sequence is convergent. Here's the explanation. Here's n, here's the things of the sequence. So n goes up by 1 at a time. And I'll sort of sketch the outline for what's going on here. So suppose that this thing is bounded, meaning that it's bounded both above as well as below. So you have your first term, which is located somewhere in here. So a sub n is equal to whatever this y value is. Now, let's suppose for a moment that this thing is monotonic because it's increasing. Then going from n equals 1 to n equals 2, one of two things has to take place. Either the value of a sub n will get larger, or it'll stay the same. If it gets larger, we can do so with something like this. For n equals 3, we have two options. It can either stay the same or get larger. And essentially what happens is if it continues to increase, it's going to wind up getting closer and closer to whatever that upper bound is. And if it doesn't increase, then its only option would be to stay the same. If it stays the same, it converges to whatever that value is that it is staying at. And if it continues to get larger, eventually it's going to run into this boundary up at capital M, and it will be able to grow no larger than that. So regardless of which case you have, it is guaranteed that it will converge to some value.